Astronomers across the globe are on high alert. For the third time in recorded history, humanity is witnessing an interstellar visitor passing through our solar system, a mysterious object now officially designated 3I Atlas. Racing through space at staggering speed, it's roughly the size of Manhattan and traveling along a hyperbolic trajectory, meaning it will never return. But what makes this discovery unlike anything before is not just the comet itself. It's what's following it. NASA and Harvard scientists have now issued a dramatic warning. Thousands of small fragments, perhaps up to 4,000 meteoroids, appear to be accompanying this object, forming an immense swarm that could sweep through the inner solar system as it passes. What began as a single point of light in the sky has now evolved into a phenomenon that could rewrite our understanding of interstellar visitors, and perhaps even of how material from distant star systems travels across the galaxy. It all began on July 1st, 2025, when the Asteroid Terrestrial Impact Last Alert System, or ATLAS operating out of Chile, detected what appeared at first to be a faint, comet-like body entering the solar system. Early data suggested a typical long-period comet, but that assumption was quickly overturned when astronomers realized that its trajectory was hyperbolic. It wasn't bound to the sun, like Oumuamua in 2017 and 2I Borisov in 2019. 3I Atlas was passing through from another star system. As more observations came in, something extraordinary began to emerge. The object wasn't behaving like a normal comet. It was losing mass at an accelerated rate, ejecting dust and gas in ways that couldn't be explained by standard cometary models. Harvard astrophysicist Avi Loeb, among others, began analyzing the data, including mass loss rates, trajectory changes, and dust ejection models, and reached a startling conclusion. The comet appeared to be surrounded by thousands of small fragments, a vast convoy of debris trailing behind it, perhaps even flanking it on both sides. This wasn't a solitary traveler. It was a fleet, a moving swarm stretching across space, each fragment following roughly the same path toward the sun. The realization that thousands of meteoroids might accompany the main body of 3I Atlas transformed what was already a historic discovery into something unprecedented. From a scientific standpoint, the implications are staggering. If true, this swarm changes everything we thought we knew about interstellar objects. Instead of a single nucleus, we could be witnessing an entire microcosmic system, a diverse collection of rocks, pebbles, and dust, each on its own slightly different path but moving together like a cosmic caravan. The cloud could extend over thousands of kilometers, widening the object's zone of influence and complicating its interactions with solar radiation, planetary orbits, and gravitational fields. The added mass and surface area from all this debris would alter the system's overall behavior, forcing scientists to abandon the simple point mass model normally used for comets and adopt a far more complex, collective system approach. The presence of a debris swarm also raises the question of collision risk. Individually, a centimeter-sized fragment poses little threat to Earth, but thousands of them, each following a slightly different trajectory, could increase the chance that some might cross Earth's orbital path. While the primary body of 3I Atlas is expected to remain at a safe distance, about 1.8 astronomical units at its closest approach in December 2025, some fragments could be nudged off course by radiation pressure or solar wind. Even a handful intersecting Earth's orbit could produce unexpected micrometeoroid events, undetectable until they entered our atmosphere. The chances of significant damage are small but not zero, and for NASA's Planetary Defense Coordination Office, the idea of a foreign swarm from interstellar space entering our neighborhood is enough to warrant serious attention. But risk is only one side of the equation. The other is opportunity. Each fragment, however small, could be a sample of material from another star system, a piece of an alien world formed under conditions unlike anything in our own solar system. Already, spectroscopic analysis from instruments like the James Webb Space Telescope has revealed that 3I Atlas is unusually rich in carbon dioxide, with a CO2 to H2O ratio nearly 8 times higher than that of typical solar system comets. This suggests it formed in a much colder, more radiation-exposed region, perhaps beyond the CO2 frost line of its parent system. If the debris swarm shares the same chemistry, we could learn how comets form in distant stellar environments. But if the fragments show variation, different ices, minerals, or organic compounds, it could mean 3I Atlas contains layers from different epochs or collisions, offering clues about the diversity and evolution of its home system. What's especially intriguing is what this debris tells us about the object's structural integrity. The fact that it's shedding so much material could mean that 3I Atlas is undergoing active disintegration, possibly triggered by heating, tidal stress, or internal gas pressure as it nears the sun. If that's true, then this swarm is evidence of a body in the final stages of decay, a cosmic relic breaking apart before our eyes. On the other hand, if the debris is organized in structured clusters or bands, it could suggest a prior fragmentation event, perhaps one that happened long before the comet entered our solar system. In that case, we are seeing the remnants of a breakup that occurred light years away, a fossilized procession from another world. As it moves closer to the sun, solar radiation pressure will push smaller fragments outward more rapidly than larger ones, stretching the swarm into elongated shapes. Over time, it could form a vast, diffuse tail spanning millions of kilometers, with dust, gas, and pebbles drifting in graceful arcs behind the nucleus. Charged particles in the solar wind could further shape this material into delicate, filamentary structures, glowing tendrils or faint halos visible only through deep exposure imaging. If the swarm continues to expand, it could create one of the most spectacular and complex interstellar phenomena ever observed, a sight that would offer clues to how comets behave under alien physical conditions. NASA's Jet Propulsion Laboratory has been running simulations to model the evolution of this convoy as it moves through the inner solar system. Their findings show that while the nucleus of 3I Atlas will likely remain far from Earth, its peripheral dust cloud could brush against regions near the orbits of Mars and Venus, and possibly, though faintly, Earth's orbital corridor several months after its perihelion, which is expected around October 29, 2025. These simulations also help spacecraft operators prepare for potential hazards, as even micrometer-sized particles traveling at hypervelocity can damage sensitive instruments. Satellite operators are quietly reviewing safety measures just in case the micrometeoroid flux increases. At Harvard's Center for Astrophysics, another team is focusing on chemical fingerprinting, developing spectral templates to distinguish interstellar fragments from solar system dust. If any of these meteoroids were to enter Earth's atmosphere, their extreme velocity and unique isotopic composition could reveal their origin. Detecting one would mark the first confirmed direct delivery of interstellar material to Earth. Networks of radar systems and high-altitude observatories are already being calibrated to look for meteor trails with abnormally high entry speeds, while balloon experiments could attempt to capture microscopic residues from the upper atmosphere. Meanwhile, ground-based telescopes in Chile, Hawaii, and the Canary Islands are devoting hours of exposure to catch faint signs of the debris halo surrounding 3I Atlas. Long exposure images are beginning to show irregular asymmetries, slight bulges, faint streaks, and curved streamers that suggest the swarm is real and far more extensive than first imagined. Each of these features provides valuable information about the comet's rotation, outgassing behavior, and the dynamics of its fragments. For planetary scientists, this represents an unprecedented laboratory in motion, allowing them to watch a disintegrating interstellar body in real time. But the most profound implications reach beyond astronomy and into the story of how matter travels between stars. The discovery of this convoy suggests that interstellar comets may not journey alone. Instead, they could carry entire fleets of fragments, the shattered remnants of ancient collisions, or the byproducts of catastrophic tidal disruptions in alien systems. If that's the case, then our solar system may be regularly visited by such fragmented fleets, most of them too small or too dark to detect. Earth could already be collecting grains of alien dust each year without our knowing it. These interstellar particles might be embedded in the lunar regolith, trapped in the atmosphere, or scattered across the upper layers of our planet's crust. This realization has extraordinary consequences for astrochemistry and astrobiology. If fragments like those following 3I Atlas carry complex organic molecules, amino acids or carbon chains, then interstellar debris could act as a delivery mechanism for the building blocks of life across star systems. The idea of panspermia, the transfer of life or prebiotic chemistry between worlds, may not just be theoretical. While survival through intense solar heating and atmospheric entry is unlikely, the very presence of organics on an interstellar visitor offers tantalizing hints that the seeds of life could, in principle, drift between stars, slowly but persistently over cosmic